If you remember, last time we were talking about the CPM method, critical path method, and we learned how to perform critical path method to identify the completion time of a project and also the critical path of the project. A critical path means the activities that has the start time and end time for which the difference is equal to the duration of the activity, so that whenever this activity is delayed, whenever something is changed in this activity so that its processing time is delayed, this will directly affect the completion time of the project. The other non-critical activities, on the other hand, have some slack time, so that if you change their duration, if you change their start time a little bit within a limit, then this will not have any effect on the completion time. But it's important, of course, you cannot increase the duration of a non-critical activity to the infinity. Okay, there is a limit on it. So if you increase, for example, 1 unit of time, then there will not be a change. There may not be a change in the completion time. You continue to increase the duration of a non-critical activity, 2 units of time, 3 units of time. So within a limit, there will not be any change. But after that, it will also start to change and shift the completion time of the whole project. Okay, so in order to identify the critical path, we learned the critical path method, the CPM method, which consisted of the forward pass and the backward pass. And in the forward pass, we start from the first node. We start from the first node, actually, which is the starting time of the first activities, which don't have any predecessors. So activities A and B, remember, the arrows in this representation show the activities, and these nodes are the starting and termination time or finish time of these activities. So activity A and B don't have any predecessors, and this one represents the start time of A and B. Okay, and in the forward pass, we start from this node and we set its starting time to be 0. Earliest start time we represent it. So in this representation, this square represents the values that we find in the forward pass, and which are the earliest start time. And these triangles, the numbers inside these triangles, are the values that we find in the backward pass, and they represent the latest start time. Okay, for node 1, we said that the earliest start time and the latest start time must always be equal to each other. And also, for the last activity, last node, again, the earliest start time and latest start time will be identical to each other. But in between, for the other nodes, they may be different. For critical nodes, they will be identical again, but for non-critical nodes, they can be different. And also, on the other hand, for some activity, the earliest start time, latest start time, earliest completion time, latest completion time can be identical, 25, 25, 13, 13. But still, this activity may not be critical, because we talked about 3 conditions for an activity to be critical. The first condition is this one: the completion time, earliest and latest completion times should be equal. The second thing, earliest and latest start times should be equal. The next thing, the difference between the completion time and the start time should be equal to the duration. If any one of these conditions is not satisfied, we said that this activity is not critical. And for this example, we solved it. We first perform the forward pass and start from this first activity. We always start with an early start time of 0. And then we look at the successors of this activity. For activity 1, 3 is a follower, is a successor, and 2 is a follower. So if you want to find the earliest start time of 3, then the thing is, for all its predecessors, you need to know the earliest start times. But look, we just identified the earliest start time of 1. Assume we haven't identified this one yet. So for 3, node 1 and node 2 are the predecessors. We only know the earliest start time of 1 and we don't know the earliest start time of 2. It means that we cannot continue with 3. After 1, we cannot find the earliest start time of 3, and we should proceed to node 2. And how do we find the earliest start time of node 2? It will be equal to the earliest start time of the previous node, which is 1, plus the duration of the activity in between, 0 plus 5. So the earliest start time of 2 is 5. Now for 3, we already know the earliest start time of the 2 predecessors. Then in order to identify the earliest start time of node 3, we simply do this. Okay, for this activity, the earliest start time is 0. Earliest start time is 0, and the duration of the activity is 6. But for this activity over here, the earliest start time is 5. We know it from here. And the duration is 3. And in order this node or the following activities to start, these two activities, activity B and activity C, must already be completed. So activity B can be completed at this time and activity C can be completed at this time. So the following activities can start after these two. So it means that we need to find the maximum of these values and set it as the earliest start time of this node, which is 8. Okay, that's why we are taking the maximum. And whenever a node has multiple predecessors, for example, this one, 1, 2, 3, there are 3 predecessors. In order to find the earliest start time of activity 6, this node 6, not activity, we need to consider all these activities F, H, and G and look their earliest start time plus duration, earliest start time plus duration, and earliest start time plus duration. Okay, so this is how we find. And in the forward pass, we simply, starting from this one, we first find this value, then we proceed to 2 and find this value. Then if you like, you can go to 3 or 4. So we are not following the order of the nodes. Whenever all the predecessors of a node is completed, you can find its earliest start time. So for 4, the earliest start time will be equal to 5 plus 8, which is 13. Then you can go to this 3, okay, and find its predecessor earliest start time, which is 8. Then since we know 3 and 4, we can find the earliest start time of 5, which is 13. And since we know 3, 4, and 5, we can find the earliest start time of 6, which is 25. So this value over here is the completion time of the project. Okay? So at the end of the forward pass, we identify the completion time of the project. And then we start the backward pass. And the starting time of the backward pass, as the name implies, we start from the last node and move backward till to the first one. And how do we start? We start by setting the earliest completion time of the project to be equal to the earliest start time. Okay, so 25, 25. And then we look at the predecessors of this activity 6, and for the activities for which we already know the latest start time of the successors. For example, look at activity 3. For activity 3, it is a predecessor of 5 and 6. And currently, we only know this value. We don't know this value yet. We haven't calculated. Then we cannot calculate this value. Okay, so it means that after starting from the last node, we cannot proceed to node 3. What about node 4? So it has two successors, 5 and 6, and still we don't know 5. So it means that we cannot proceed to node 4. So the only alternative is to move to this node 5 and find its predecessor, find its latest start time. Okay, so how do we find it? This node 5 has only one successor, so it means that we only need to look at this one, and we look its latest start time, which is 25, and then we subtract the processing time of the activity in between, which is 13. Okay, so 25 minus 12, the start time is 13. Now, when we know the start time of this node 5 and 6, we can proceed to 3 or 4, whichever we like. Again, I'm repeating, we are not following the order of the nodes. Before proceeding to 4, we can proceed to 3 because we already know the start times of node 5 and 6. And for node 3, which has two successors, how do we find this value over here? Simply, we look at the latest start time of activity 6 minus 25 minus the duration of activity in between, which is 11. And we look at this activity, the latest start time of activity node 5, 13, minus the duration of activity in between, which is 2. So what does this imply? This is the latest start time. And it says that if you start this activity 3 later than this value or later than this value, then the completion time of the final activity will be affected. Okay? So it cannot be later than this one. It cannot be later than this one. Since we are looking at which one is the later, it cannot be later than this, it cannot be later. What does it mean? It should be less than or equal to this one, and it should be less than or equal to this one. And actually, this indicates that we need to take, or we need to find the minimum of these two. Okay? Otherwise, if we don't take the minimum of them, then the other activity will be late, and this will affect the completion time. And from here, we see that it's 11. So we find this value. Again, for 14, we look at the start time, latest start time of activity 5 and 6, and the duration in between. Remember, this dashed line represents a dummy arc with a duration of 0. So 13 minus 0 from this side, 25 minus 1 from this side, and the minimum is 13. And we move in this way, and when we reach to the first node, node 1 in this example, it should be 0. Okay? If it is not 0, then it means that you did a mistake. You need to check your calculations because always the starting node will have the earliest and latest start times equal to each other and 0. Okay, this is what we did until now. And by checking the 3 conditions, okay, we identify the critical path, and the three conditions are this. The start times, earliest and latest start times are equal to each other. Earliest and later completion times for this activity A are equal to each other. And 5 minus 0 is equal to this duration. So it means that this activity is on the critical path. Look at this activity B. Is it critical? So it is earliest and latest start times are equal to each other. Earliest and latest completion times are not equal to each other. So B is not critical. What about C? Again, since these two values are not equal, it's not critical. What about D? These two values are equal. These two values are equal. 13 minus 5 equal to the duration, so it is critical. For activity, this dummy activity, these two values are equal, and the difference is 0, which is equal to the duration. So this is critical. By the way, there may be more than one critical paths. Okay, so there may be alternative critical paths. It's not necessary to only have one critical path. Okay, keep this in mind. In this example, we had only one alternative, but in another example, we may have multiple critical paths. Okay, and then for activity G, is it critical? Look, this is 25, 25. This is 13, 13. Good. But 25 minus 13 is not equal to the duration, so this is not critical. And if you follow in this way, we see that the critical path is this red path. And now the next step is, this is the CPM method. And from this CPM method, we need to assign these activities to a timeline, to a Gantt chart, to see the starting and ending times of the critical and non-critical activities, and how long would it take to complete this project. So how do we do it? First of all, for the critical activities, the start and end times of these activities will be equal to their designated start times. So for activity A, this is critical. So the starting node of activity A is 1, and ending a node for this activity A is 2. So from here we understand that activity A starts at time 0, and with a duration of 5, it ends at time 5. So these times in this example are given in terms of days. Okay, so it takes 5 days to complete this activity A. And now look, for activity A, this is the time axis, time in terms of days. And activity A, this is 0, this is current time. When activity A starts here, it takes 5 days and it's completed at time 5. There is no slack. This is critical activity. And then continue with the critical path. And for D, we see that it starts at 5 and ends at 13 with a duration of 8. So starts at 5. Okay, this is 5 starting time, and ending time is 13. And again, look, this activity is not critical. And it is critical, but the thing is, it is a dummy activity. We placed that activity in order to avoid such a situation. So these two activities start and end in the same node. We said in our previous lecture that this is not a valid representation to perform CPM. So therefore, instead of representing it in this way, we included another node and we added a dummy node and represented this activity in this way. So because of this, we have this dummy activity. This is not an activity, so we don't need to represent it in our Gantt chart. Okay, so this is Gantt chart. We call it Gantt chart, which represents the activities, their starting and completion times on this time axis. And then the next critical activity is activity H. It starts at 13 and ends at 25 with a duration of 12. So it starts at 13 and ends at 25. So when you start from these critical activities and follow the critical activities till to the end, this will represent the completion time. I mean, the durations of the activities on the critical paths, when you sum up them, it will be equal to the completion time. On the other hand, for non-critical activities, look at activity B. So from here we understand that it is earliest and latest start times for activity B is 0. And from here we understand that its earliest completion time and latest completion time is 11, which means that if this activity B is completed before time 11, then we can complete the project, we can still complete the project on time if it is before time or day 11. So it means that this activity B can start at time 0 immediately, and as long as it is finished before 11, then we are good. There is no delay in this project. And we know that its duration is 6. So for activity B, the starting time can be 0 and the completion time can be 11. So it will be somewhere in between. Because of this, we show it with a dashed line. So this activity B with a duration of 6 can be anywhere in between. So usually we start it as soon as possible at time 0, and we say that activity B starts at time 0 and ends at 6, and it has a slack time of this difference, which is 5 units of slack time, which means that if this activity B is delayed for 5 days, still we can complete the project on time. Okay? And as you can see in this representation, we actually did not show where this activity B starts. We just show the earliest possible start time and latest possible completion time. So this activity B will be somewhere in between. Similarly, look at activity C. So its start time is 5 and its completion time will be the latest of these two, which is 11. So as long as we complete this activity C before 11, then we are good. And if you look at this difference, 11 minus 5 is 6 units, but the duration of the activity is 3 units. So it means that there is a slack. So look at this activity. It can start at time 5, and as long as it is completed at time 11, then we are good. So if you start this activity C at time 0, it will be completed at time 8. I mean, not 0, at time 5. If we start it at time 5, it will be completed in day 8. And from 8 to 11, we have slack time. Okay, so as long as this activity is delayed less than 3 days, then we are good. We continue to place all these activities in a similar way. For activity E. For activity E, look, its start time from here, since we are looking at the maximum length or the time span of this activity, when we are considering the start time, we look at the earliest start time, which is 8. Okay? And then when we are looking for some activity, when we are looking for its completion time, then we are looking at its latest start time for this node. So in between 8 and 13, this activity E can be placed, 8 and 13. And its duration is 2. So it can start at time in day 8, and as long as it's completed before day 13, then there is no delay on the project. So between this 8 and 13, there is a time span of 5 days, but the duration of this activity is 2 days. So it means that there is a slack of 5 minus 2, 3 days slack. As long as the delay in this activity E is less than 3 days, then we can complete the project on time. And the thing is, look, while I'm saying that as long as this activity E is delayed less than 3 days, we are on time and etc., I'm assuming that the only delay is in this activity. Because if there is a delay in this activity B, and a delay in activity C, and a delay in activity E, and etc., if all of them are delayed at the same time with different amounts, then we may have a problem. We may have a delay in the project time. Okay, so these slacks are, when I say there is a slack of 3 days for this activity, I'm just assuming that the only delay will be in this activity. Okay, now we learned how to perform this CPM method, how to find the forward pass, backward pass, the earliest start time, latest start time, and the critical path. And also we learned how to sketch the Gantt chart as a result of this CPM. We can also formulate this project scheduling problem, or the CPM, as a linear programming formulation. And instead of using this forward pass and backward pass, we can identify the solution with this LP formulation. And actually, this formulation is very similar to what we already learned, because we already learned the shortest route problem, in which we try to find the shortest route between a starting node and an ending node, and there is a network in between. So we try to identify the shortest route from the starting to the ending. But in CPM, what we try to do? We try to find the longest route, not the shortest route, but the longest route from the starting node to the ending node. Okay, the completion time of all activities will be equal to the longest route. Okay, if you just take the shortest route, you will find that, okay, these activities will be completed in this time, but there are still other activities which are not completed yet. In order this project to be completed, all activities must be completed, and all activities are completed when you look at the longest route. And it means that we will use exactly the same formulation with the shortest route problem, but we will just change our objective function. Instead of having a minimization objective, now we will have a maximization objective. Okay, that's it. So we define the decision variable exactly the same way as a shortest route problem. And remember, in shortest route problem, what we did? We said that, okay, we try to find the shortest route between node I and node J. And in this case, we assume that in this short node I, there is an inflow. There is an inflow of 1 unit of activity. Okay, and there in the destination node, we assume that there is an outflow of 1 unit. So for this one, we try to find or we solve the problem as a maximum flow problem. Just a minute. Yes. Okay. So again, Xij, according to this formulation, it will represent the amount of flow in activity Ij for all the arcs, for all the activities defined as Ij. And in the shortest route problem, we had the distances, and now in this project scheduling, we don't have the distances, but we have the durations. The difference is this. Okay, so instead of minimizing, we maximize. Instead of multiplying the distances with the flow, we are multiplying the duration with the flow. Every other thing is the same. So whenever we are considering a flow optimization, at each node, the total input flow should be equal to the total output flow. These are the constraints. Okay, and again, we will use the same representation of such a table to formulate the problem. So we will not write the constraints in this way, but we will represent our formulation with this tableau. But let's have a look at this example. We already solved this problem, and let's develop the LP formulation for this project scheduling problem to identify the critical path and the completion times of the activities. Okay, so what do we do? Look, this is the starting node, and we will assume that there is an inflow of 1 unit here. And this is the termination node, and we assume that there is a 1 unit of outflow in this one. So according to our formulation, we just say that this our objective is maximize. Look, this is 6 times x1 3. Why this is 1 3? Because this is arc 1 3. And then for this one, it is 5 times x1 2 plus 3 times x2 3, and etc. We write all of them. And then subject to, we write the constraints for each node. For node 1, the inflow is 1, should be equal to the outflow, and outflow is equal to x1 2 plus x1 3. So this is for node 1. For node 2, inflow is x1 2, should be equal to the outflow, which is x2 3 plus x2 4. And we write these for all the nodes. And when we represent this with such a table, so for each arc, look, these are the arcs, and arcs are the activities. Okay, so the columns represent our decision variables, which represent our activities, and the rows represent the nodes. There are 6 nodes. The first one is our objective function. Okay, so for x1 2, the coefficient is 5. x1 3, the coefficient is 6, and etc. So our objective is to maximize this multiplication plus this multiplication plus this multiplication till to the end. And for this node 1, I told you that there is 1 unit of inflow, and this 1 should be equal to x1 2 plus x1 3. Okay, so if you like, as I told you, you can multiply this whole thing with a negative value, which will make -1 equal to minus x1 2 minus x1 3. These two are exactly the same thing. So in this tableau, if you like, you can write it in this way. If you like, you can write it in this way. But we said that we can represent this inflow as negative for this, and the outflow as positive, so that we understand where we start and where we end. Okay, so if you see negative value here, it means that it's the starting node, and starting node is node 1. And if it's positive, we understand that node 6 is the ending node. And therefore, in order to write this value -1, I write this value, this version of the constraint. So it means that x1 2 and x1 3 has -1 coefficient. Okay, all others 0. Now look at node 2. Okay, so inflow x12 is equal to the outflow x23. So x12 equals to x23 plus x24. But we said that in this representation, we collect every decision variable on one side of the constraint so that the right-hand side is always a constant value, which is 0. So therefore, we have 1 for x12 coefficient, -1 for x23, and -1 for x24. Okay, so x23, 24 negatives. So this is how we formulate the problem. And for the last one, last node over here, this x36 plus 56 plus 46 will be equal to 1. 36, 46, and 56 equal to 1. Okay, and when you give this model, of course, you cannot give this table into the Cplex. We will give this model into Cplex, and when you solve it, we identify the completion time to be 25. Then we identify x12, 2, 3, 4, 5, and 5, 6, their values to be equal to 1, and this identifies the critical path. Okay, the critical path. All others will be 0. It means that you will not be able to find the earliest and latest start times of the activities in this way. We will just identify the critical path and the completion time of the project in this way, okay, by this LP. But if you use the CPM method with forward and backward passes, you will find their earliest and latest start times also. Okay, now we are going to solve an example problem. Just a minute. Yes, so we will, let me make some space here so that we can work on it. We will consider this example and first sketch its network diagram and then use the CPM method to find the critical path. Okay, now how do we do it? Let's have a look. We have these activities A, B, C, D, E, F, and G. We know their predecessors, we know their durations. And we start, while constructing the network, we said that we will represent each activity with 2 nodes. Okay, so activity A will be something like this. And the duration of this activity is equal to 10. And we start from the activities which doesn't have any predecessors, A and B, but I don't start sketching until I get the activity with the first predecessor. Look, activity C has this activity A as a predecessor. Okay, so what does it mean? It means that if I represent this activity A, let me sketch like this. If this is activity A, and whenever it's completed, then this activity C starts. Okay, and the duration of this activity is 3. And then look at activity D. For now, I just ignored activity B because it doesn't have a predecessor, and until now it is not a successor of anyone. So I just sketched this activity A and C. Now I continue with D. It has this C as a predecessor. It means that whenever the C is completed, D starts. and the duration of D is 3. Sorry, the duration of C is 5. Not 3. This is 5 from here. And the duration of D is 3. Now I sketch this one. Now E, its predecessor is D. So whenever D is completed, E starts, and the duration of E is 2. Okay, I sketched this one as well. Now look at activity F. It has as a predecessor B and E. So E is here, and I also need to have B. But until now, I didn't represent B. So let me represent B in this way. Okay, so this is activity B. And then both of these activities will join together to represent this activity F, right? So is this the correct way to represent it? Where is activity F? Is this activity F or is this activity F? Remember, the activities are the arcs, not the nodes. And both E and F, okay, both E and B should be a predecessor of this activity F. So actually, this is not the right way. I am sketching this because I know that you will do these kind of things, these kind of mistakes during the exams. Okay, so thing is, since E and B are the predecessor of activity F, it means that these two activities should end at the same node so that it will be the predecessor of F. Okay, and it has a process time of 1. So it means that this should be activity B, ending at the same node with activity E. But where it should start, if I start here with another node, then I need to add another dummy node for A and B so that this project start with such a single node. But actually, I don't need to do that because it's unnecessary. If I just start this activity B from the same node as activity A, then it's okay, there's nothing wrong with this one. Because remember, our restriction is this. If there are two activities that start and end exactly with the same node, then we don't want this situation. But look, A starts with this one and ends with this one. B starts with this one and ends with this one. So there's no problem. So I can start the activity B from the same node with activity A. And now I sketch this activity F, and we have this activity G. And look, for activity G, the predecessors are E and F. Okay, now it's confusing. How can I do this? Because look, E is a predecessor of F, and then E and F should be a predecessor of G. So it means that this E and F should end at the same node. And if they end at the same node, how can E be a predecessor of F? Actually, here you need to be careful. This is critical. Since E is already a predecessor of F, then actually this E over here is unnecessary. It's unnecessary because when I sketch this activity G like this, you see F is a predecessor of G and E is a predecessor of F. It means that E is already a predecessor of G. So this E over here is unnecessary. Okay? So this representation now is correct. Don't be confused. Whenever one of the activities is a predecessor of another activity in this way, then you don't need to keep both of them as predecessors of another activity. This E is just unnecessary here. And this is it. This is the network. And now on this network,
Doctor.
Yes.
Instead, if we write E and F, if we write D and F, how it will be?
Here you mean as the predecessor, instead of it was
Yes.
E and F, if it was D and F, right?
Yes.
Okay,
Yes.
it is the same idea. Look, D is a predecessor of E, and E is a predecessor of F. So it means that D is already a predecessor of F. And again, D is unnecessary. You don't need to write it. You just look at the last predecessor, okay, which is F. And if you say that this F is a predecessor of G, then that's okay. You conveyed that information. Okay. So here, even if it is A or C or D or B, all are unnecessary. If you just keep F, that's enough. But if there is any other activity, let's say activity J, J and F are predecessors of G, then it means that you need to have another activity G coming to here from some other node, okay? But if an activity is already sketched as a predecessor of one of them, then you don't need to keep the other one. That's unnecessary. Okay, now this is the representation. And after this representation, you can just start naming the nodes, and we can say that this is node 1, okay? These are important. You can start even here and saying node 1, but of course it will be confusing why you are starting in the middle, okay? So 1, 2, 3, 4, 5, 6, and 7. And when you write these names and also the duration of B, which is 7, now this is the network. Okay?